Now we get into our first theorem of the chapter, so theorem 5.1, chapter 5, the first item in the chapter. Remember that Sipser uses global ordering, which is something I highly approve of. I wish many other authors did. As I process textbooks for future courses, many of them don't use global ordering, and it's a real pain when I'm trying to find page numbers of some theorem or whatever it is that is referred to later in the text. I'm hunting through, trying to find where the thing that is referred to, where is it, which page is it on, and hunting it down is a pain if you don't have global ordering. Right. Okay, so here's the theorem statement. It's this language. Remember, we're now working on language in the sense of a set of strings. We're working on languages that we'll try to show, using theorems like this one, that there are a whole bunch of languages that are undecidable. And here's our first example. We'll use a proof that a particular language, like halt, this one, is undecidable. Now, to me, I still have a bit of a question mark myself. Perhaps it hasn't gelled fully enough in my own mind, I'm not sure. My question mark is, to what extent is this proof, when you see it, is it about reducibility, and how much is it just by contradiction, proof by contradiction? We've done a lot of those in the past. Now, this chapter, in proving a lot of languages, we'll see more and more as we get into the chapter, that these languages are undecidable. Typically, the kind of proof that we use to show that, to prove that these languages are undecidable, is proof by contradiction. So it's a proof method that we will use heavily. Here's our first example for this chapter, and we've been using it quite heavily already, you're probably aware. Okay, so the proof idea down to square and a half before we get on the actual proof. How to prove that this language, halt TM, is undecidable. And just a bit of quick revision. What is halt TM? It's the language consists of ordered pairs, M, W. M is a Turing machine. W is the input string to that Turing machine. And the condition that that ordered pair belongs to the language, halt TM, is that M halts on input W. Right? Now the Turing machine can halt for two different reasons. One is that it accepts the string, or it rejects the string. Okay. Right. So proof by contradiction. So now, what we're originally trying to prove is that halt TN is undecidable. So if we're going to prove that by contradiction, we, as usual, we assume the opposite. Okay, so halt TM is undecidable. In other words, it's decidable. And if a language is decidable, there is some Turing machine that decides it. Okay. And the contradiction we're trying to derive, because proof by contradiction, you always have to arrive at some kind of contradiction. Well, if we assume that halt is decidable, then we will derive that a TN is decidable. Now we know that that's not the case, that's the contradiction. So this proof boils down to proving that if halt TM is decidable, therefore ATM is decidable. That's what the proof is essentially about. Okay. Now we know that ATM is undecidable because that was theorem 4.11 that we spent so much time on in the previous lecture. Okay, and that theorem is on page 176 of your text. Right, this is a statement by Sipser. So he's saying the key idea from the previous session, I'll say it again just for revision purposes. So if you have two problems A and B, and problem A is undecidable, so assume you know that, then if you can reduce A to B, then B is undecidable, but no proofs given. So we're using that idea, what I've just said, to show that, so this is our problem A, ATM, is reducible to problem B, which is halt TM. Okay? We know that's undecidable, and if we can reduce this to this, therefore we know that halt is undecidable. Now my question mark is, that's what he says, but the actual proof, is that what he's actually doing? And to what extent is the notion of reducibility coming into the proof? Now, maybe I need to digest on it a bit more, but it's an interesting question, because maybe see if you can answer those questions I've just posed. All right. Okay. So so we've seen the opposite of this. Therefore, halt TM is decidable. Right? So that means there is a Turing machine that decides it. Let's call that Turing machine R. Okay. And by definition, that Turing machine R decides this language, because we've assumed this is decidable. Right. Now we're going to use R. This is part of the proof. This is a proof idea. We're going to use that Turing machine R that decides this language as a component, a part of some larger Turing machine, called that S. Okay. And we will have this Turing machine S that uses R as a part, calls on the use, it uses R. This machine S, we will show, actually decides this. That's the strategy of the proof, because we're trying to, if R exists, if R decides halt, then we can construct a large Turing machine S that decides ATM, and that would be our contradiction. Right? That's the strategy of the proof. Now let me see, thinking real time here. So R and S, I guess there's some kind of reducing going on there, right? So I suppose you're saying that S reduces to R, or was it the other way around? See, that's why I get frustrated with Sipser. He doesn't. There's too much between the lines. Too many things implicit, unstated, which is frustrating. So perhaps a bit more thought. Anyway, so question for you. Given this, where's the reducibility come in? Is R being reduced to S, S being reduced to R? I suppose by the end of the chapter, if I go back and look at this, that will become more obvious. Anyway, question mark for the moment. Alright. Okay, so you got the picture. We're assuming halt is reducible, therefore there's a Turing machine that... We're assuming halt is decidable, therefore there's a Turing machine R that decides it, called it R. And then R is going to be a component, a part of some larger Turing machine S. And this Turing machine S will decide ATM, and we'll show that. And of course that's the contradiction, because we know this is undecidable. Alright, so how do we construct S? Sort of moving on the proof. Well, when you're trying to prove things yourself, often it pays. It's a useful trick to pretend that you are the Turing machine in question. How would you go about solving this problem? Okay, so imagine, pretend you're this machine S, So how would you go about deciding this this language ATM? So if you're given this input, right? Because that's an element. Yeah, that's the typical format of an element of this language, right? It's this ordered pair. And ATM, these ordered pairs, these elements of this language,